Hi, in this video we're going to talk about the idea of continuity, and we will get to the formal definition, but we're going to start by just talking about the idea. And so there are a bunch of graphs here. These are graphs that we looked at before when we first started the calculus material this semester, and there's a few more down here as well. But we're going to just look at these graphs, and we're going to notice how these graphs have various kinds of behavior at and around x equals 1. And so that's what we want to focus on here. All right, so one important thing to notice about these graphs here is that in these examples, some of these graphs have a break in the graph at x equals 1, various kinds of breaks in the graphs at x equals 1, and other graphs, the ones that I did not circle, contain the point 1, 1, and as x gets close to 1, the graph gets closer and closer and closer to that point. So that's the main idea of continuity. I'm just going to write the idea here and then we'll look at the definition below. But we say a function is continuous at some value. Here we're going to focus on x equals 1. In the definition, we'll look at a generic value of x if there is no break in the graph. All right, so mathematically, we need to define what we mean by this idea of a break in the graph, and so that's what we have down in the definition below. So all of those graphs that I circled in pink there have a break in the graph at x equals 1, and then the three that I did not circle, so graph A, graph B, and graph F, notice that at x equals 1 there is a point, and as we get close to x equals 1, the graph is headed toward that same point where the graph is actually at when x is actually equal to 1. All right, there are a few more graphs down below here, and these also all have breaks at x equals 1. So one important thing to notice about these graphs is that they have different kinds of breaks at x equals 1, right? So some of them have asymptotes, dashed lines on the graph. Some of them have just a hole in the graph, a missing point. Some of them have like two pieces that don't match up. So there's lots of different kinds of breaks in the graphs around x equals 1. But all of those ones, except the ones I marked in green here, except A, B, and F, all of these others have a problem with continuity at x equals 1. All right, so I've alluded to what the definition really is here when I drew these pictures and focused on the point at and around x equals 1, that on these three that I marked in green, notice that at x equals 1 there is a point, and that point is the same as where the graph is headed when x gets close to 1 on both sides. All right, so we've already talked about all of those ideas. We just didn't call it continuity, but if you look down below here, you see the definition of continuity. A function is continuous at x equals a, so that's just a generic value of x. You might use x equals c or x equals x naught or whatever, but just at some specific value of x, if, and then there's this last part here. So you need to be able to memorize this. You should be able to state this and write that down. So there's really three parts to that. And I'm going to just kind of start here at the back because that's what I did when I was talking about the graphs up above. So I noticed that there's actually a point or an output of the function at x equals a. And then the other side of the equals here is about what's happening when x is close to a. So that limit exists. And then the other key part of this is what's happening in the middle is that those things have to match up. So they agree or they are equal. So the point at x equals a is the same as the limit as you approach x equals a from both sides. All right, so sometimes this definition is really written in those three parts, and in our textbook, there is something called the continuity test, which is really just a restatement of that definition with those three parts there. So I'm just going to write that here. And this is really just kind of a way to check for continuity, but it's really just a restatement of the definition. All right, so our textbook calls that the continuity test, but again, that's really just a restatement of that definition of continuity. All right, there are a couple of other vocabulary words here, but we're going to go ahead and look at some examples and kind of talk about what we've discussed so far, and then we'll come back and talk about these vocabulary words. All right, so here we have a graph of a function and several different questions about that. And you would not necessarily have to think about these questions in this order. This is just the order they're asked here in this example. All right, so the first one here asks us to think about the domain of f of x. So that's really just asking us about input, output values. So we're stating all of the x values for which there is an output. So when I look at a graph, I tend to focus on places where there might be problems with the domain. So there are several places on this graph where I would notice that there's something interesting going on. All of these places I highlighted. The other important thing when you're thinking about domain is paying attention to what's happening sort of at the ends of the graph. So where these arrows are at, kind of at the edges of the graph. So all those places that I just highlighted are where my eye would go when I'm thinking about really any of these three questions here. Okay, so we're going to start by focusing on those places, and all of those places I highlighted for answering this question about domain. What I want to pay attention to is, are there any points there, any y coordinates for those specific x coordinates? So one thing that we should notice is that when I think about the domain, I'm going to need to exclude x equals -1. There is an open circle on the graph right there, which means there's not a point there. And looking up and down the graph at x equals -1, I'm going to have to exclude that. There's no points anywhere that have an x coordinate of -1. At x equals 0, there's an open circle in the graph at 0, 4, but there is a point at x equals 0. It just doesn't kind of match up with that part of the graph. So there is actually a point that has an x coordinate of 0, but that is another place I would sort of pay attention to. Kind of a similar thing happens at x equals 2. Notice there's an open circle here, so there's not a point there at 2, 5, but there is a point down here with an x coordinate of 2. So x equals 2 is in the domain of the function. All right, the next place I highlighted is at x equals 3. And we see this dashed line, so vertical asymptote there on the graph at x equals 3. And you might notice that there's not actually a point there at x equals 3. So that's another value that I'm going to have to exclude. So you wouldn't necessarily have to write down what I've written here, exclude x equals -1 and 3, but those are the things you would notice when you look at this graph. All right, the other thing I would notice on this graph is that there are no other breaks in the graph really. There's no other places in the graph where the graph stops or has strange behavior. I would also pay attention to the ends of the graph, the arrows, kind of at the two ends at the left and right side, and those indicate that the graph is going to continue on in that same fashion that we already see there. So we're going to assume from those arrows that the graph is going to continue on forever to the right and also forever to the left. So the only values that I need to exclude from the domain are x equals -1 and -3. So if I give the domain an interval notation, I'll just start here with -infinity up to, but not including -1, then union -1 to 3, union 3 to infinity. So that is not new information. Technically, domain is something that is old information, but when we think about domain, what we're really thinking about is the part of continuity that's asking us to think about where does f of a exist. Right? That's what domain is really about, that there's an output for those values for input. All right, and then the next two questions here are the two sort of flip sides of the same question here. One is asking about where the function is continuous, or asking about continuity of the function. And then the second one is asking us to find values of x where the function fails to be continuous. So it's asking us about discontinuity of the function. All right, so I actually would probably start by answering the question for 3 and then use that to write the intervals on which the function is continuous. Okay, so when I think about where a function might fail to be continuous, I'm really looking for those three things that we listed in that continuity test. Where the function fails to exist, where the limit might fail to exist, and or where those things might not be equal. So when we answered this question about domain, we were already identifying places where the function output does not exist. So those two values, x equals -1 and x equals 3, those are places where the function fails to be continuous because f of a does not exist. I could also say that f of -1 or f of 3, those values are undefined. That's just another way of saying that same thing. All right, the second thing I need to think about though for continuity is where the limit might fail to exist. And so again, all those places on that graph where I initially highlighted would be places that we might want to look at and think about the limit existing or not. Those are all places where the function's doing something kind of weird. All right, so at x equals -1, we know that our function is discontinuous there because f of -1 does not exist. But let's just go ahead and check those other conditions and think about those other conditions. So when I think about the limit as x approaches -1, you see that as you approach -1 from the left and the right, the limit actually does exist. So that's not a reason the function is discontinuous there. I'm just going to put a note there though. So note that the limit does exist. That will actually help us answer one of these later questions here. So at x equals -1, the only part of the definition of continuity that fails is that f of -1 exists. All right, the next place when I'm looking at the graph where we see a problem with continuity, something strange going on or a break in the graph, is at x equals 0. So we do have a break in the graph there at x equals 0. That's understanding the concept, being able to look at the graph and notice that there's a break in the graph at x equals 0. And then the theory part is understanding from the definition which parts fail. All right, we can see here, I'll just put out here to the side in green, that we can note, we actually already discussed this, that f of 0 actually does exist. That's 1. But you can see when you look at the graph, as you get close to x equals 0 on each side, the graph is headed toward different places there. So that limit, though, does not exist. Limit as x approaches 0 of f of x, I'll just abbreviate here, does not exist. All right, so that's the only reason that that function is discontinuous at x equals 0. It's about the limit, not about the function output. All right. The next place on this graph where I see a break in the graph, where I highlighted when I initially looked at this graph, is at x equals 2. All right, so at x equals 2, I do have a point, so that's not the reason. So I'm going to write out here that note that f of 2 is -1, and that does exist. The other thing I might note is that when I get close to x equals 2 on both sides, those y values are headed toward the same place, 5. So the limit as x approaches 2 of f of x, that also exists. All right, but we clearly see a break in the graph at that point. So that is one of them where that third condition, that they are equal, is really the reason. So there's a couple ways I could write this. I could say the limit is 5 and the function output value is -1, and these are not equal. I could also just say that the limit does not equal the function value. I actually kind of like writing it out a little bit better this way because it's clear that you know what these values are and you're clear about the condition that's not met. All right, and then the other place on this graph where we have a discontinuity is at x equals 3. And we already said that f of 3 does not exist. You can also look at that graph and see that as you get close to x equals 3 on each side, the function is going different directions. So that one has kind of a second reason why it's discontinuous there. There are really two conditions that fail. Sometimes in the My Math Lab homework, it'll ask you to choose all the reasons a function is discontinuous at a point, and sometimes it just asks you to give a reason. So if you only need one reason, either of those two reasons would work. But if you're asked to choose all the reasons, this one does not have an output at x equals 3. It also does not have a limit. Notice that it doesn't really make sense to talk about equality, that third condition, being equal or not, if the two things that you're considering do not exist. So notice on all of these others, I didn't really talk about they are equal. That really only makes sense to check that third condition if the two things that you're talking about actually exist, so you can check to see if they actually are equal. All right, so intuitively, looking at the graph, x equals -1, 0, 2, and 3 are the places where I see breaks in the graph. So those are visually the places where I notice discontinuities, and then I can go back through the definition and give the reasons for those discontinuities. All right, once I've answered that, then it's easy to state the intervals of x on which the function is continuous. I just need to state the intervals of the real number line that exclude these values of x. So I'm kind of visualizing a number line when I do this. So you start on the leftmost at -infinity, and let's see, we will get up to -1 first, and then -1 to 0, and then 0 to 2, and then 2 to 3, and then 3 to infinity. So anytime I'm really asked to state intervals on which a function is continuous, I generally start, whether it asks me this or not, by thinking about the values of x where the function fails to be continuous. So even if it doesn't ask that, that's a good way to start that question. All right, let's look at those other two vocabulary words, and then we'll come back and look at these last two questions on the example. So we talked about in these graphs up here above that we started off by looking at that there are a lot of different kinds of breaks in the graph at and around x equals 1. And so there are a lot of different ways to classify those discontinuities. Our textbook talks about some, or you might watch some other videos that talk about lots of different ways to classify those. But really, going forward, the most important distinction is classifying discontinuities as removable or non-removable. And I'm going to highlight the three in these pictures that are removable discontinuities. So there's one on graph of E, one on the graph of G, and one on the graph of L. And those are the ones that are considered removable discontinuities. So I want you to focus for a second on those three graphs and notice the reasons why those functions are discontinuous at x equals 1 and how that's different from all the other functions that are discontinuous at x equals 1. Okay, so if you thought about that, one thing you should notice about those three that I said are removable discontinuities, that in all three of those, unlike the other ones that are discontinuous at x equals 1, the limit as x approaches 1 of those functions does actually exist. But the function has a discontinuity for one of two reasons. Either there's no point at x equals 1, or there is a point in the case of E, but it's in the wrong place. So conceptually, that's the idea of a removable discontinuity, when the limit exists, but there's no point, or the point is in the wrong place. The other way to think about this is that removable discontinuities are easy to fix. And by fix, what we mean is essentially you can fill in the hole. And so you can take away the point that's in the wrong place and fill in the hole by redefining a point. Or if there is no point, just define a point to fill in the hole. And doing that is what's called a continuous extension. So let's go down here to the vocabulary and write that down. So removable discontinuities, if the limit exists, but f of a does not exist or does not equal the limit. All right, so that's what a removable discontinuity is. And if we define a continuous extension, we're going to do that by redefining a point so that it's actually equal to that limit. Let's go ahead and do that, and then we'll come back and talk about this last vocabulary word. All right, so it asks us to classify each discontinuity as removable or non-removable. So we can think about that graphically. We can also think about that using the definition. So the removable discontinuities would be the ones that are easy to fix by just redefining a point that would fill in the hole. So visually, there's one of those at x equals -1. I could fill in that hole by just defining a point. And then there's also one at x equals 2. I could get rid of the point that's in the wrong place and then redefine it so that that point fills in the hole. Notice that the other discontinuities, this one at x equals 0, which is called a jump discontinuity, by the way, but notice that I couldn't just redefine a point to fix that discontinuity, right? It would require major surgery on this function to repair that one. Whereas the removable discontinuities, it's just a little patch, a little band-aid that can fix those. Same with the other discontinuity at x equals 3, that I can't fix that discontinuity with just a little band-aid. That would require major surgery to fix that. So that's just a little conceptual way to think about those removable and non-removable discontinuities. So my two removable discontinuities are at x equals -1 at x equals 3. And the reason those are removable is because those are the two where the limit does exist, but the function is still discontinuous for one of the other reasons in that definition of continuity. The other two then are non-removable. All right, and then the last part here asks us to create that continuous extension. So we're going to fill in the hole. And we actually could do that at x equals -1 and at x equals 3, but it really just asks us to do that at x equals -1. So there are a couple different ways you could write this, but essentially to answer this question that it's asking us here, really all I need to do is I need to define a new point at x equals -1 with, I'll use function notation here, f of -1 equals whatever the output should be that fills in that hole. So let's go up here and look at the graph. That's going to be, I want that output to be 2 to fill in the hole. Notice that here, when I wrote down that limit, that is telling me what I want that function output to be. If you don't have a graph of the function, you're working with the equation, you can find the limit, and then that's what you want to define that output to be. So I want f of -1 to equal 2. All right, so that's essentially all I need to do to answer this question. There are some times where they might want you to write that in function notation. Our textbook uses a capital F of x to define a continuous extension of a function, little f of x. So we would use whatever the function equation is for little f of x. We don't have an equation, we just have the graph here. So I'll just write little f of x. So I'm going to use that function everywhere except at x equals -1. And then I want this new function to have an output of 2 when x is actually equal to -1. So I used a piecewise function notation here to define this new function, capital F of x, that is the continuous extension of little f of x at x equals -1. All right, one more vocabulary word to talk about very briefly here, one-sided continuity. So if I go back up and look at some of these original graphs that we were talking about, and instead of focusing at x equals 1, let's focus at x equals 0. And we might notice that if I compare, for example, functions a and f, that at x equals 0, there's not a break in the graph on either of those at x equals 0, but I have to talk about continuity at x equals 0 a little bit differently for f than I do for a. And that's because the domain of the function only includes one side of x equals 0. So we can also talk about one-sided continuity, left continuity, or right continuity, but you can use just the appropriate one-sided limit to talk about or to define continuity if the domain only includes one side of a point. So in the case of function f here, we might talk about this function at x equals 0, and we would say that that function is right continuous at x equals 0 because f of 0 exists, and it is equal to, here I would just use the right-sided limit. X approaches 0 from the right of f of x. And the reason I might do that for a function like that is because the domain doesn't even include the left side, so it doesn't really even make sense to talk about the left side at x equals 0. Most of the time when we talk about continuity, though, we're going to be focusing on both sides, but occasionally you might see a theorem later that talks about right continuity or left continuity of a function. All right, there's some other videos with some theorems about continuous functions, so check out that next.